Let's continue with the introduction of VAR. As mentioned at the end of the last lesson, there are two major approaches for the estimation of VAR, the non-parametric approach and the parametric approach. Let's first talk about the non-parametric approach. It is the most general method that makes no assumption about the shape of the profit and loss or the return distribution. Let FV be the probability distribution function of the future portfolio value V at risk horizon H. Then, the worst possible portfolio value V star at confidence level C can be determined by solving the probability of V less than or equal to V star is equal to 1 minus C, where this probability can be calculated by integrating the probability distribution function F from negative infinity to V star. Let V0 be the initial portfolio value and R the rate of return for the risk horizon, which is a random variable with mean mu and standard deviation sigma. Then, the portfolio value at risk horizon, denoted by V, is equal to V0 times 1 plus R. The portfolio value V star corresponds to a particular rate of return R star is then equal to V0 times 1 plus R star. Let VAR with the subscript R denote the relative VAR, which is defined as the dollar loss relative to the mean on the horizon. More precisely, it is equal to the expectation of V minus V star. Substituting in the expressions of V and V star in terms of the rate of return R mentioned in the previous slide, we get the following simplified expression, where mu is equal to the expectation of R. The absolute VAR, denoted by VAR with the subscript A, is defined as the dollar loss without reference to the expected value. More precisely, it can be calculated by V0 minus V star. Writing V star in terms of R star, we obtain the absolute VAR is equal to minus V0 times R star. For short horizon, with negligible expected rate of return, the absolute VAR is approximately equal to the relative VAR. Here's an example. The following diagram is the historical distribution of company ABC's daily profit and loss, where the horizontal axis is the profit and loss in $1 million, and the vertical axis is the number of days. That is, each rectangle describes the number of days for a particular profit or loss to occur within the time horizon of concern. Note that the profit and loss is equal to the current portfolio value V minus the initial portfolio value V0. And for a particular portfolio value V star, its corresponding profit and loss is denoted by P and L star. From the previous diagram, we can see that the average profit and loss is equal to $5.417 million. Since the total number of observations is 254, to calculate the VAR at 95% confidence level, we need to determine the profit and loss star such that there are 12.7 observations to its left. In the sorted list of observations, the 12th observation is minus $2.652 million, and the 13th is minus $2.498 million. A linear interpolation gives the profit and loss star being minus $2.544 million. Therefore, we can get the relative VAR and the absolute VAR at 95% confidence level, respectively, as follows. Next, let's introduce the parametric VAR. In this case, the profit and loss, or return distribution, is assumed to belong to a parametric family. Then, VAR can be obtained via parameters of the distribution. This simplifies VAR computation. However, an issue of concern is whether the distributional assumption is realistic. For now, we set this issue aside. In the following, we examine the case when the rate of return R follows a normal distribution. Suppose the rate of return R follows normal distribution with mean mu and standard deviation sigma, Then we have the portfolio value V also follows normal distribution, whose mean and standard deviation can be calculated correspondingly. Same as the non-parametric case, the worst possible portfolio value V star at confidence level C is solved from the following equation. Here, the probability that V is less than or equal to V star is equivalent to the probability of R is less than or equal to R star. Since R follows normal distribution with mean mu and variance sigma squared, standardize the random variable, we get that the probability is equivalent to the probability of a standard normal random variable Z is less than or equal to minus alpha, where minus alpha is equal to R star minus mu divided by sigma. Alternatively, this value is also equal to the cumulative standard normal distribution function evaluated at minus alpha. With alpha being minus R star minus mu divided by sigma, we have R star equals mu minus alpha times sigma. Now, the relative and the absolute VARs can be expressed in terms of the distribution parameters of R as follows. We list the several frequently used lower quantiles of the standard normal distribution in the following table. If the distribution parameters mu and sigma are annualized, and the risk horizon is delta t, given in years, then the relative VAR and the absolute VAR can be calculated respectively by the following formula. The above method generalizes to other distributions as long as all the uncertainty is contained in alpha. For example, a student's t distribution with 6 degrees of freedom has alpha equal to 2.57% at the 99% confidence level. When market risks are being considered, typically VAR is computed for a time horizon of 1 day. Assuming that the returns on successive days follow IID normal distributions with mean 0, the VAR for the n-day horizon can be approximated by applying the square root of time rule. That is, the n-day VAR is equal to the 1-day VAR times the square root of n. Now let's take a look at an example. Suppose that the daily profit and loss of a company has been found to have an annualized volatility of 12%, and its current worth is $20 million. Assuming normality of the profit and loss distribution and 250 business days in a year, can you determine its 95% relative VAR for 1-day horizon and 10-day horizon? As given in the question, V0 is equal to $20 million, sigma is 0.12, and the time horizon delta t is 1 over 250. Thus, by the formula introduced in the previous slides, we can obtain the 1-day 95% relative VAR for the company as follows. Note that the lower quantile alpha is equal to 1.645 for 95% confidence level. By the square root of time rule, the 10-day VAR is equal to the square root of 10 times the 1-day VAR.